draft physics video on the big subject, the biggest blunder in the history of science. Yeah, maybe so. At least when you think in terms of the modern age and the fact that we don't have really excuses for making such a blunder when you have so much information and so much context. It's one thing for the ancients to come up with, wrong ideas. It's another thing for, people who do have a volume of information to make kind of mistakes of arrogance, let's say, or enthusiasm. So anyway, gravity, big problem. So I guess we will start with Newton. Obviously it starts before then, hundreds of years of not even getting the sun in the right place and all that stuff. But again, can be excused because there wasn't a volume of information to pick at in terms of understanding the difference between, say, forces and matter, and making distinctions between the little bits and the clumpier bits and all of that. Alright, so we'll start with Newton's equation. Everybody's always so obsessed with this math crud. So this equation doesn't tell you what the gravity on Earth is. It doesn't do much, really. It just converts some idea of a relationship between, this is the distance. It's not really the r squared. It's kind of a deception because it's the distance squared and between the two objects' centers. And the masses are the two objects you have in your equation. So in a sense, Newton's equation was dependent on a two-mass equation. You couldn't do the equation with one mass and find the force created unless you wrote a different equation. And the g is just a made-up little constant to turn it into a force number that would be like how many ounces of carrots does a rabbit have to eat to jump 15 feet in 1 second. And that's all it's doing. It's just giving you an arbitrary amount of something, whatever you decide the force is. So in this case it was Newton's, and so Newton gets to make up the constant and blah blah blah. So anyway, that equation could be rewritten as the force is the mass of the one object plus the mass of the other object divided by 2r, or 2 diameters of distance between them. And if you want to do one object, how much force is the one object creating, then it would just be m1 divided by the distance. So it's just a clear relationship between how far away they are and how much they weigh, and the assumption is that they're spherical objects. So the math only works on spheres. I mean, precisely. It'll not work if the objects aren't spherical. And the relationship between spheres is that if you double the amount of stuff, the volume, so it's equally massive, and you just increase the volume. So you make for every atom, you just create another atom. You just double the amount. In a sphere, that ends up creating 4 times the circumference, which just means that that's the inverse square law. So the inverse square law, as stated, is just a consequence of spherical geometry. So spheres end up making, so you can sort of understand, if I put a bunch of polka dots on a balloon that's blown up this big, and I blow it up twice as much air in it, the polka dots will separate from each other by the inverse square law. They'll stretch. So they'll go 4 times. So twice the air, 4 times the distance between the dots. And so that's the inverse square law. Alright, so the glaring problem with most equations you look at in science is there's nothing stopping this from going infinite. So I can have an infinite mass and an infinite mass and an infinite distance if I wanted to. And obviously that would be impossible to calculate, but I just mean the implication is that this force is unlimited, that you can have as high amount of it as you want, that there's whatever's creating it can be, you can just keep making more of it. Okay, there's no finite end to how much of this you can do. And you know, as humans, we certainly know I don't have infinite force. I can't do the Superman thing or underdog. You know, I can't just take more and more pills to get stronger and stronger, to do stronger and stronger things. It's finite. It has a limitation, and then you're done. It used it all up. The wind can only blow so hard, kind of a thing. You know, the speed of light has a constant and end. Speed of sound has a constant. Well, that's a little different. Certainly it's not different for how fast something can move. There's a barrier to how much speed things can acquire. And I would argue that all the forces, those things are all reflections of forces and reflections of the fact that you exhaust the capacity for the force. You use up what you're creating in the force. And in some things it's about vibrating things and how fast you can actually vibrate them without it becoming circular, so to speak. Alright, well, I don't want to get too complex. So this is the Wikipedia page on gravity, and I thought it was probably worth reading it just to point out that every bit of it is just wrong-headed and wrong. So let's understand that, okay, the argument being made is so Einstein's theory isn't any better in the sense that it still creates this infinite amount thing. There's no acknowledgement that the force is coming from something. The other irony is Newton's calling it a force when it's not considered a force, because there's nothing generating the movement. The movement is being considered as some kind of thing outside of normal physics. There's no, you don't have to burn something or in any way release energy. No nuclear bombs created, you don't even have to light a match to make the earth move towards the sun, or the sun towards the earth. Nothing to push them, nothing to incite them. And I just said the magic word push, where everywhere in the regular physics it's sort of understood that yes, it's a push universe, except for gravity. Almost everything else you can find where there's a change in pressure and it's lowering pressure, you know, that creates, it's the push from the outside. The thing that stops the balloon from getting bigger is the air pressure pushing on it. There's always some countervening force. If you see something moving towards you, it's usually because it had a little rocket engine that pushed it towards you. It's not coming towards you because it's pulling. So that's a starting point where you say, well, that's reason to pause and say, well, why would gravity break that consistent rule? But no one paused. And again, you know, even Newton didn't pause at recognizing or speculating, as far as we know, as far as I know, regarding how much of this force you can create, how big you can make something. So you can get to that argument sort of by recognizing what's happening in gravity. So another problem with the way people think of this equation, they think it's related to a feather and a hammer moving at the same speed when you drop them without an atmosphere, so that mass doesn't somehow matter. But clearly mass matters to the force. So what's the truth is that if you hold a feather over your head and you hold a 10-pound weight, a 10-ton weight over your head, you're going to notice the difference, and you're going to notice that it has nothing to do with the atmosphere in a sense, that there's something else making the 10-ton weight seem much heavier than the feather. And that's because the force is the force equation isn't the bit that has anything to do with what acceleration is. Well, yeah, it does. Just sorry, I have to think. This is why I'm making this video. It's the practice video, because it, the relationship between the difference between the feather and the 10-ton weight is that each atom is being moved the same with the same amount of force, and obviously the 10-ton weight has a lot more atoms, so there's more collectively force that has to be applied to move the 10-ton weight the same amount of distance you're moving the feather. So that this force equation basically confirms that mass matters. It's not irrelevant, but it's irrelevant to what we see as the movement, because we're not seeing the force required to push the 10-ton weight. But you would see it if, like, say you were in space or something and you tried to move a feather, accelerate it. If you had to accelerate a feather or accelerate a 10-ton weight in space, you'd find that flicking your finger at it, the 10-ton weight's going to move pretty slow, and the feather will go to the moon. It's off, it's gone, it's flying, zooming. So that relationship is the one that these equations don't account for, in the sense that what I'm trying to get to is the same argument I was making about this circular thing where you double the volume and you create 4 times the circumference. The same thing happens in the inverse with pressure. So as you compress something, the pressure increases, and in the center, because it has all that weight above it, kind of thing. And so the real problem with having some sort of gravity system that doesn't have limitations is, the real limitation is going to be your chemistry starts to break down. You can't maintain any normal chemistry under the pressure that would be created in the center of the Earth, for example, by the massive amount of stuff moving above it. The mass of the stuff moving may be moving slowly, but it's moving with a force that's unstoppable, so to speak. It's incredibly high torque, if that's a way to say it. And all the chemistry starts to break down under that tremendous amount of pressure. And then once you can break down chemistry, okay, you start smashing compounds and creating too much pressure and heat for them to survive, you'll eventually can get to some sort of nuclear disaster where you start crushing the atoms themselves. There's so much weight on them, so much pressure, so many atoms stacked on top of them, so to speak. Any movement at all by a stack that big is not something you can stop. Like I said, if some force is going to move a 10-ton weight towards me 1 inch, so you think of it as one of those rooms where the walls are coming in and they're going to crush you. So a 10-ton weight is going to move 1 inch. There's very little you can do to stop 10 tons of mass if it's moving. So once it's going, you're going to have no chance, your flesh, of doing anything to stop it. And the same thing is going to happen to the atoms inside of any planet that gets very, very large in terms of its mass. Is the stuff in the center isn't going to be able to resist the pressure, and it's going to be crushed. Alright, so that's enough of that, I think. I don't know if there's any other mathematical principle has to be gotten to, but there's nothing fancy about the math. There's nothing, this equation is not anything but defining the relationship between how far you are away and how much you weigh is how much force it would require if you had to provide the force. That's all it's saying. If you had to make the force, how many carrots would you have to eat to push the Earth the amount it moves towards the sun in a given amount of time? And that's all it is. It's not. It doesn't provide a perfect microscopic lens to the truth or something. It's not getting at something. It's just describing that simple relationship that gravity works that way. The closer you are, the more you're affected by the potential of the thing moving, and the further you are, the less you're affected. And the more mass between you and the center of gravity, the more you're going to be, that's defining the potential of that object to influence you. So you can just sort of understand, the further away I move a light bulb, the less capacity the photons have to hit you. Fewer and fewer of them will. Alright, so that's not exactly, I'm not saying it's not profound, I'm just saying it's not where you stop, certainly. It doesn't really answer any questions about what happens, why is it doing it. So the big answer was Einstein's relativity, his spent space, his theory of the force is just something that happens. It's just something space does. So all I have to do is take a piece of matter, any size, and pop it into the universe, and it automatically, without doing anything, is applying force from no source. It just has it because it has something called mass. Now the trick is, mass can only be measured by, technically, by measuring its gravity, something's gravity. Now we can cheat because we can know there's stuff inside of atoms, and we can just count how much of that stuff there is, and then just say what the weight is, because we're just going to count the stuff and say that whatever constituent stuff that goes with that must go with that, and that's sort of the explanation. But as I've stated in previous videos, gravity is really a nuclear force. There's the small bits are the things that actually have to do the moving. So it's just a kind of a basic logical exercise where the fundamental, if I was to break it down into some sort of fundamental understanding, you can understand that there might be two things in the universe. There might be the force bits, like light, that have a constant speed. And you would say those things have perpetual motion, in the sense that the force bits, like a photon, they don't ever disappear. So like a little bit of infrared radiation, for example, or anything you want to describe on the electromagnetic spectrum. Whatever little thing goes out, that little thing never stops moving. So if the photon hits something, it moves, the energy of that photon moves through the thing just as if the photon didn't hit anything. I mean, it doesn't lose any of its substance, and it will eventually pop out as a little piece of infrared radiation light, and it'll fly across the universe again and go somewhere else and move inside of it, and then pop out and move somewhere else and move somewhere else. So a photon lives forever. It never dies. It just perpetually moves, this kind of idea of the speed of light, and it just travels through things just like that. And everything that we would call a force, I think, is doing exactly that. So whatever's, by physics doesn't give you a statement about what's causing magnetism, but the little bits of magnetism are doing the same thing as the photon. They move into something, they cause a definite effect, things move inside the matter, the atoms move, something moves, and that movement will precipitate in the future somewhere a release of exactly what went in. So what goes in eventually comes out. And those kind of conservation laws physics is comfortable with. The problem is you can't have conservation that's only one-ended, one-sided, where you create a source of energy, movement, but you don't have any definition of where it came from. So you're starting with something that just that instigates the creation of a force, but it doesn't consume any force, so to speak. You don't have any evidence of the origin of the force, because it's not something that's already in the system. It's just created by the placement of mass in the universe. Alright, so it's more reason to think that these aren't really the right answer, because what the Earth is doing by moving towards the Sun is it's consuming a force. Force goes in, and force will eventually come out. If the Earth hits the Sun, you'll see a lot of force come out, and that's the force the Earth absorbed by moving towards the Sun. The force it took to move the Earth is exactly the force you're going to get out when the Earth hits the Sun. So it's storing it, it's capturing it, and their model doesn't really have any mechanism for that capture beyond what they think of in terms of the momentum, in the sense that yes, the Earth has acquired more mass, in a sense, more substance because it's moving towards the Sun, but they didn't account for where it came from. They're just saying geometry put that extra stuff into the Earth that the Earth now can release. So I'm just saying it sort of breaks that continuity. So the idea is that if you understand the universe to be the little tiny things, which are the force bits, so that would be the little stuff that's, say, pushing the stuff inside the atoms together. That's probably too much to ask, as a starting point, because people don't understand force that way. But I mean, I think the electromagnetic spectrum of all the little photons, the ton-type forces, is a good place to start, because they can be understood as discrete little bits moving the speed of light. And once you understand that the magnetons, the stuff that makes magnets work, the virtual photons that physics creates to illustrate the movement of the force, if you think of those as being real, and you say to yourself, well, where did they come from? So then you have another source of force, and you don't have a definition of where it came from. And so now you can tie magnetism to gravity, in the sense that they're both using a force they don't account for. Magnets don't have to they don't have to eat any carrots to create this light that comes out of them, this energy that comes out of them. That's why they call it virtual, it's because they can't account for its existence. And the same holds true for the nuclear bits. They have no way to account for what they call charge, the attraction and repulsion between electrons and protons. They have no mechanism describing why an electron moves towards a proton, or why two electrons would repel each other. So there's no accounting for the existence of the force. They allow the force to exist, in terms of they realize that the force will have an impact, and that it will keep moving through a system. So if the thing does have that force and it is moving, they'll account for the fact that that movement will be expressed in not just a virtual thing, but in a real effect change. And they'll just, because conveniently what will take place is the magneton will be converted into energy they recognize the existence of. So when the magnetic field moves, which is really just having a bunch of these little bits move in a particular way to push things, that pushing will be turned into movement or heat, things we accept as being real forces, even though the thing that caused it they don't consider a real force. Alright, yeah, that's probably not as sexy as I need it to be, but whatever. Like I said, this is mostly just for my benefit, so in terms of trying to help other people understand why the current model is fundamentally flawed. Not, it's not superficially flawed, but substantially flawed in very fundamental ways, where it doesn't account for the flow of force. It doesn't obey the rules of conservation in terms of the creation of this fundamental element of force that's created by the existence of these bits, in the sense of the it starts in the atom with the relationship between a proton and electrons. In terms of that force is the same force that essentially expresses itself as gravity and magnetism. So anyway, so unification it also just points to the fact that you need something that does unify, because they're all lacking explanation in the same way. What's the source? So my alternative explanation is the source is, yes, a field, a universe full of pressure created by little bits moving just like photons, except they're invisible. You can't see them. You can't measure them with any. The instruments we have don't detect them. Just like if you tune your radio to a certain station, it's only going to be responsive to certain frequencies, and it's not going to see the others. I mean, there's probably lots of examples of selective detections in a range. Our eye would be an example. It only sees photons with a certain frequency, and that's it. Anything with a little bigger frequency, a little smaller frequency, it doesn't see them. It doesn't detect them. We don't see radio waves flying around. We don't see anything else with our eyes, because the detector doesn't see them. So some things need a special kind of detector. And the trick is with gravity. I mean, obviously we can see the detector. We can see an effect. But the problem is what moved this pen was the force affecting the little bits inside. And that we can't see. We can see this big thing falling, but we can't see the little bits that are inside that are actually doing the moving and are actually being pushed by the force. So the force is hard to detect because it's hard to make an instrument small enough. It's impossible, pretty much, to make an instrument small enough to actually see the force, because all we can see is the effect on something bigger than what the force is actually acting on. So yes, so obviously that could exist. Something could exist that doesn't affect anything but the little tiny bits, and it's affecting them basically in this first magnetic way, in the sense that they're polarized, and because of that polarization there are certain rules that I'll explain in other videos, but it just has to do with simple rules of motion, and by those simple rules you can create circular motion, square, 4 right turns, and store force. And that's what matter's actually doing, is storing force. So when the Earth moves towards the Sun, what it's doing is collecting force. So force from the outside was going to hit the Earth and move towards the Sun. So there's this field of energy. The energy, essentially from everything's perspective, no matter where I put something in a field of energy that's even, pressure, the pressure is going to be around it equally. And when you move 2 bodies into that field of pressure, it's like putting 2 bodies in a field of light. They'll cast shadows on each other. But and so the effect of those shadows you could think of as being an absence of agitation in the direction that the shadows cast at. So wherever the shadow is, so say there's lights, there's a big round ball we're living in, and the lights are all on the outside circumference of the round ball, and we're two things inside that big sphere. You can understand that there'd be a certain amount of shadow I would cast on, say you were the other person, I was the other person. I would cast a certain shadow on you from the directions of how my volume was expressed. And we're not spherical, so the rules of regular gravity aren't going to apply. But the point is there'll be a shadow cast. And the shadow just represents where stuff that was going to hit you doesn't hit you. Now, the trick is, if we can turn that light into something like gravity that actually forces something to move because it consumes it, then you can understand how it propels it, and I wouldn't have to use it just as an analogy. I could use it as an explicit description of how it actually works. But this is pretty much how it actually works, is that the only part that matters, the shadow, wouldn't be created if the thing, the light, didn't get absorbed by me, not just reflected in some passive way, but reflected in the real world way that if I throw this pen at the camera, the force of the pen's going to bounce off and the camera's going to move. And the rules of nuclear reactions are sort of the same way, is that the force is conveyed from one thing, from the pen, into the other thing through a kind of conversion of one thing having the motion, the other thing accepts the motion, except in the real universe it's a kinetic thing. So it's like two kinetic balls swinging and bouncing into each other, and they keep their own motion, but they change their direction. So they keep their velocity, they just switch direction where they were moving. That's what's happening on the nuclear level. So it's not like a common reflection, it's a kinetic reflection that takes place on the nuclear level because of this difference between force and matter. So that's what I was trying to get to before, is this understanding that the force bits are all the bits that move perpetually. So they're constantly moving the speed of light, they never really stop. And the matter bits, which are a complex arrangement of, you could say, force bits in perhaps circular traps. Those bits don't have any perpetual motion this way or this way or this way or this way. Their motion is trapped inside of this circle. And so to move this circle in a direction, to take this circular trap and move it, requires you to essentially update this circle into a new position, and then update it to a new position. So you actually have to add more going this way than went this way. And to make it perpetual is more complicated in the sense that you have to have more what are called matter bits in the side that the motion's in. But the point is you're moving, matter doesn't have any perpetual motion besides the motion of the force bits it's made out of. But there is a distinction between these two things. So when they talk about gravity, they don't make those distinctions. So they think something like a photon has gravity. They think because somehow it has this quality of being an exister, and that anything that's an exister is going to bend the fabric of the universe. It'll have gravity and it'll be affected by gravity. Now, one of the obvious reasons not to believe that is light doesn't slow down because of gravity, and it doesn't speed up because of gravity. So in its forward and say backward directions, gravity has no effect. So they're just saying that, okay, you can't make it go faster, but you can move it side to side, and that's a continuity problem. You say, okay, well, why the difference? Why that standard? That doesn't seem complete. You have a rule that says it can only do this, but it can't affect this other dimensional move. Why can it affect it in this dimension, but it can't affect it in this dimension? and the conclusion would be that no, the force bits they are gravity. They're not being affected by gravity. They're the pressure. They're the thing creating the thing that will be absorbed by something that will give it motion. So say this pen is hit by a photon. In truth, what happens is the photon can be absorbed by the pen. So it can stay inside of this pen because it gets in one of these little traps, these circular traps, and it can stay inside of there. And the truth is, because of that, that motion can be spread over this entire pen and move it a very tiny bit, 1/1,000,000th of the width of a photon kind of movement, but it's there because it's in there. That motion went in as a this, and technically, somewhere in the universe, this has to be released again. It's in there, and that's fundamentally how gravity works, is that this external pressure pushes things in the sense that the thing absorbs it. It hits it, the thing gets what it had, so the pen can be thrown at me, the pen falls, technically. Like I said, in the kinetic world that doesn't happen, but anyway, and I have the motion inside of me, whether it's just in the form of a vibration for now, or if it actually moves me forward. But the point is, you can still see the movement of the pen is still in me, or it's expressed in the fact that I move. But you'll see an expression of it. And when I move, I push a bunch of other stuff. I push the atmosphere, and if there's something near me, I push it, and the force goes into it. So the force doesn't ever stop. It just keeps traveling. So in gravity, what's happening is the shadow, as I was speaking about in the light example, the shadow is just an illustration of what the other body has absorbed. So the shadow I would cast on you is basically defining how much energy I absorbed, and the shadow you cast on me is defining how much energy you absorbed that didn't get to me. The photons were coming at me, they didn't get to me, and created a shadow on me. And that's a definition of a less pressure hitting me from this side than was hitting me from behind. So I move forward because there's less things pushing me one way than pushing me the other way. And that's basically how gravity works. So it's when I move, I create the shadow. When I absorb force, then the force can't get to you. So when a body in space moves towards something, that's when it's creating gravity. Because in a sense, it's going to force the other object to move towards it, because it created a shadow on it. It stopped force from getting to the other object, so the other object ends up moving towards you. So when something moves towards me and absorbs a force to do it, the force pushes it. Again, it has to absorb something to move. That absorption means I didn't get hit by it. You did. Okay? And me not getting hit by it means I'm going to be pushed towards you. So gravity is essentially an inductive force, and the more I move towards you, the faster you're going to end up moving towards me. And so when the Earth moves towards the Sun, what's really happening is a substantial piece of the mass of the Sun moves towards the Earth. Now the trick is the Earth is rotating, so you can sort of understand that each time the Earth pulls the Sun, it pulls it in a different direction. So the Sun is moving, but it's moving in a circle in the end. So it ends up back where it started, because the poles are all in a different direction, and they're opposite each other. So at one point in the orbit, the Earth will pull the Sun up, and at the other end of the Earth's orbit, it's going to pull the Sun back down. So it ends up equaling out when you go a full circle. And so all the forces end up being zero again, and you can do the whole thing over again. But in fact, that's what the sun's doing. For all the distance in terms of bending the Earth's path, so all the Earth moves off of its straight line path, the sun moved an equal amount of its mass, moved. So as many Earths are moving towards inside the sun, as much mass as the Earth is moving towards the sun is moving towards the Earth. Right. So the center of the sun's gravity is always in motion. It's basically the mass is moving around the center of gravity more than the sun is moving. So it's like the mass of the sun is not in the center of gravity, so the mass is moving around the center of gravity, and that mass changes its where it's going, how fast it's moving this way versus how fast it moves this way, but it all ends up in some sense balancing, except the sun does actually move some, and that's what causes the precession problem with Mercury. But anyway, so that's probably enough for this video. Like I said, just kind of practice. This is so fundamental, and it's such a fundamental mistake. So I'll probably do a part 2 where I'll actually read these couple of paragraphs, because yeah, there's just nothing. it's not even close to the right answer. What's really happening. So anyway, till the next time and such.